All right, everybody can see and hear me and get the slides and all that. Just
Okay, looks good. So we
making,
start.
okay. All right. Well, thanks for that introduction, Grisha, and thanks to everyone for being here virtually. My name is Brent Graner, and I'm going to be telling you all today a little bit about the cyclotron radiation emission spectroscopy, or CRES experiment, that we're currently putting together here at CENPA at the University of Washington for purposes of looking for new physics in precision measurement of high energy beta decay spectra, particularly for the case of the beta decay of helium-6. And I chose to subtitle the talk Precision Nuclear Physics with Microwaves since, as Grisha mentioned, my own background is in precision measurement in the context of atomic physics, where there's a long history of using microwave techniques and also getting very precise results. So I thought that there was some interesting historical context to the idea that microwaves are now being used to really push the precision of nuclear physics experiments. So I should also say that I tried to keep the talk fairly brief and pitch it at a fairly introductory level to allow more time for Q&A. So if you have any questions or you feel like I've glossed over something, feel free to interrupt. Don't be afraid to unmute yourself and holler at me. Don't bother holding questions till the end. Okay, so before I get into talking about our experiment, I want to contextualize the talk a little bit. This is a slide that I took from one of my CENPA colleagues, Jason Hempstead, who successfully defended his thesis here at CENPA in connection with the Fermilab muon G-2 experiments last summer on Zoom. I know you've all probably seen this result, but I want to make sure that it's front of mind just to emphasize the fact that there's now a discrepancy between the standard model predictions and experimental observations that's grown to over 4 sigma. And it's really getting to the point where nobody can afford to downplay the likelihood that there's something big that is potentially going to be found fairly soon. And I would argue that that gives us very good motivation to go looking for other small deviations from standard model predictions, especially in the context of weak sector physics. That being said, our project is looking for evidence of small deviations from standard model predictions in the context of weak sector physics. More specifically, we're looking for tiny distortions to the standard model predictions for the energy spectrum beta decay electrons. It turns out that we have the means at our disposal to observe microwave radiation emitted by individual electrons that are circling in a strong magnetic field. And we can use the connection between the energy and the relativistic cyclotron frequency to measure the energy spectrum of an ensemble of radioactive helium-6 atoms or other radioactive atoms. I should also point out that all of the pioneering work in the CRES technique was done by our collaboration here at the University of Washington, known as Project 8, who really developed this technique for the purposes of indirect neutrino mass measurements by making a very precise measurement of the endpoint energy of tritium beta decay. We're very fortunate to have them here at UW with us, and almost none of the progress that we've made over the last 4 years would have been anywhere near as great as what we've accomplished were it not for them kind of showing us the way forward, or at least to our first events. So I'm an experimentalist, and as such, I don't want to go too deep into the theory, but I will say on a fundamental level, we want to look for hypothetical scalar and tensor contributions to the weak interaction. The helium-6 beta decay is primarily sensitive to the tensor component, and those hypothetical tensor interactions are parameterized by this dimensionless Pfirtz interference parameter, which is rather dryly named little b. The standard model prediction for little b is 0. This being high energy or fundamental physics, excuse me, I should point out that people at the LHC are working along similar lines, and we expect that our result can be competitive if we can get a measurement on the Pfirtz interference coefficient little b with a sensitivity at a level of 10 to the minus 3 or less. So that's kind of our initial goal, and we believe that really pushing the CRES technique can help us reduce that uncertainty down to the level of about 10 to the minus 4. Okay, so I mentioned that we want to measure beta decay energies, and at this point you may be asking exactly how that relates to this Pfirtz interference little b parameter. This is a plot of the standard model energy spectrum for helium-6 beta decay electrons. You'll notice that the Lorentz factor here, gamma, gets to be fairly large due to the high kinetic energy endpoint of the decay at about 3.5 MeV. And it turns out that this high energy is actually one of the things that makes helium-6 a good isotope for our measurement, because any non-zero value or any non-standard model value of little b will give the spectrum a characteristic distortion that goes as m over e, where m is the mass of the electron and e is the total energy. So picking an isotope that gives us a wide range of energies gives us kind of a long lever arm to examine the distortion across the spectrum and help improve our sensitivity. And this is just a graph of the expected distortion to the spectrum for a value of little b at 10 to the minus 2 relative to the standard model prediction with little b equal to 0. You can see that if little b is positive for helium-6, we expect a surplus of events relative to the standard model at low energies, and correspondingly a deficit of events at high energies. Okay, so that beta spectrum is what we want to measure, or how we make the measurement little b and search for these scalar and tensor couplings to the weak interaction. And this is a conceptual overview of how we want to go about actually making the measurement. So if we can detect the radiation that's given off by an individual electron, as I said, that's orbiting in a strong magnetic field, all we really need to do is make a series of broadband Fourier transforms and then stack them up horizontally into this kind of spectrogram and identify any bins in each time slice that have power above threshold. So this cartoon here is just a representation of that spectrum. It's actually a three-dimensional plot with frequency on the vertical axis, time on the horizontal axis, and power being the third axis. We can simplify that a little bit just by plotting the bins that have power above some predetermined threshold. And if there's an electron that's inside of our apparatus and radiating microwaves, that will have they will peak at some distinct frequency. And as that electron radiates or loses energy due to radiation, the frequency will go up, because you can see here in the formula for the cyclotron frequency, the kinetic energy is in the denominator. So that electron goes about radiating energy and increasing in frequency, and getting smaller and smaller in cyclotron radius. And eventually, what might happen is it might collide with a residual gas molecule, undergo some scattering process, and then go on re-radiating with slightly less energy and correspondingly higher frequency. So every so often you can see these jumps in your event. And just to familiarize you all with the jargon, we make sure to refer to these individual line segments on our spectrograms as tracks, and the set of all tracks that are made by an individual electron we collectively refer to as an event. So obviously our task in measuring the beta decay spectrum is identifying the energy of each electron at the moment when it's created. So the whole task in our analysis here is to identify the first track in an event, and then identify the initial frequency with which the electron started emitting microwaves. So measuring the electron energy based on a frequency is advantageous for quite a few reasons. Most notably, except for these occasional gas collisions, residual gas collisions, we avoid a lot of complicated energy loss mechanisms that you would get with a traditional beta decay spectrum measurement. We don't have to go around modeling all of the ways in which our electrons can rattle around in some plastic scintillator or a germanium detector or a tank of liquid argon or what have you. It's essentially a massless detector, and the relationship between energy and frequency is known almost perfectly. So the frequency-based measurement is a very advantageous way to make the measurement. It turns out the magnetic trapping efficiency is energy independent, and the high frequency resolution also means that we have Professor Shallow on our side as well. Okay, so this slide lays out some of the most basic points of magnetic trapping for charged particles, which we confine with a simple magnetic bottle. That in this case is just a set of coils that's wound around a cylindrical decay volume where the helium-6 atoms are confined. And those coils combine to create a small dip in the magnetic field, which is directed along the axis of the decay cell. And then if you consider everything in the adiabatic limit, you find that the flux inside of an individual cyclotron orbit is a conserved quantity, as is the total energy. And from there, you can work it out that the electrons are confined based on what we call the pitch angle, which is the angle relative to perpendicularity with which the electron is emitted. So we end up trapping electrons in a fairly narrow range around 90 degrees, those that are emitted perfectly perpendicular to the holding field, which is again along the axis of the waveguide. And that trapping condition is based on the pitch angle and not, as I said, on the total energy. And the acceptance range of that pitch angle of the set of electrons that will be trapped gets wider as you crank up the current in your trap coils. Okay, so that's kind of the conceptual version of what we want to measure, and this is kind of a cartoon schematic of the real version. Basically, everything on this slide boils down to some kind of plumbing, either for microwaves or heat transfer or radioactive gases. We have about 10 to the 10 helium-6 atoms per second coming off of a liquid lithium target here at CENPA. Those atoms diffuse down a large 8-inch pipe towards our apparatus, and then get compressed into this cylindrical decay volume that I was talking about a little while ago. So that cylindrical decay volume is part of a waveguide apparatus. It's spaced off from the rest of the waveguide by some capped-on windows that are transparent to microwaves that just enable us to get a better control of the vacuum inside the decay cell than everywhere else in this apparatus. If the electrons are emitted close to perpendicular to the magnetic field that's generated by this superconducting solenoid here, those electrons will go whipping around at the cyclotron frequency. They emit microwaves along the axis of the guide. And then we have the waveguides here taking off the radiation in either direction and directing it onto a pair of low noise amplifiers at about 5 Kelvin here. So those low noise amplifiers need to be kept near liquid helium temperature to keep their thermal noise down to the level above which we can see signals at 1 femtowatt, which is about the order of magnitude of the size of individual electrons' radiated power. So once we get the signals out of these cold amps, we mix them down by about 18 gigahertz to make them easier to digitize. Obviously, we can't digitize things directly that fast, and then run them into an FPGA-based data acquisition or DAC platform, which has a pair of analog to digital converters that are capable of sampling at 5 gigasamples per second. So we can theoretically get an observable bandwidth of about 2.5 gigahertz out of this setup. So instead of looking at 18 gigahertz directly, we're looking at more like 18 to 20 gigahertz as our sort of phase 1 design target for the frequency window that we can see. Okay, so we're getting a little bit more towards some show and tell here. This is basically a scale model or scale drawing of the apparatus as it actually exists. You can see the cylindrical decay volume here is towards the center of the magnet bore. We're piping in helium-6 or some other radioactive gas via this long titanium tube. The helium-6 enters through these little holes in the waveguide, and then there are trapping coils wrapped around this guy and a bunch of waveguide components that convert the circular polarization of microwaves emitted by the circular orbiting electron to linear polarization that can be conveyed by rectangular waveguides, and then the low noise amplifiers here on the left, coupled to the second stage of this cold head here, that's situated in this main cryostat. So that's what it looks like in the model. This is what it looks like when we all put it together, or put the whole thing together. You can see this is the amplifier box. The amplifiers sit at about 5K, coupled to the second stage of this cold head. The first stage of the cold head is about 40K. That couples to this copper cryostat. We stuff this full of super or multi-layer insulation when we want to run it. And these WR42, these rectangular waveguides, convey the microwaves from either side of the decay cell to these sets of cascaded low noise amplifiers. And then the low noise amplifiers gain up the signal by about 60 decibels and pass them to the ambient receiver chain via these insulating stainless steel cables. Okay, so that's kind of the amplifier side. This is sort of the business end of the apparatus. This is the insert that ends up inside of our magnet bore. You can see the way we put together the decay cell itself, the magnetic trapping coils that we wound around that decay cell, the circular to linear polarizers that take the circular polarization and convert it into linear polarization that can be conveyed by these rectangular waveguides, so we're not losing power. The rectangular waveguides that lead back to the amplifiers here on the top right. some copper bars to make sure that everything can stay reasonably cold, and the wires that make sure that we can monitor all the relevant temperatures and turn the trap coils on and off. Okay, so it turns out we put it all together, and would you believe the thing works? We got our first CRES signals from metastable krypton 83 atoms in, I believe it was April of 2021. You can see that all these diagonal lines are effectively individual tracks from electrons that are radiating in our apparatus. We used a fairly aggressive trap depth for looking for our first set of events, so there's quite a few to be seen here. And you can see that there are individual events where you can kind of pick out with your eye, individual scatters where electrons collide with residual gas molecules and make these characteristic little jumps that distinguish tracks from events. And one of the things that we wanted to go about looking for once we saw our first CRES signals was whether or not this made any sense. We used, like I said, we're using this metastable krypton 83 source that is a source of a bunch of conversion electrons. The energy of those conversion electrons is dependent on which atomic shell they were ejected from, either the K, L, M, or N shells. This is a reference table from Ali Esfahani's thesis from Project 8, because they're using a very similar calibration source for their apparatus, or identical, I guess, calibration source for their apparatus. And we can see with a very kind of naive analysis, we can see clearly distinguish the K, L, and M and N lines from this krypton source. I say this is kind of a naive analysis because we did no event reconstruction here. That was essentially taking this data set and running it through our processor, treating each one of these tracks as if it were an independent event. So don't take this as a final result or anywhere near it, but just with this kind of maximally naive analysis, I wanted to make the point that we can get pretty good energy resolution in and of itself. Our frequency resolution is about 36 kilohertz on top of an 18 gigahertz signal. So part per million resolution on frequency is pretty much easy. And the energy resolution is about 1.5 keV if you separate this L line from the M and N lines. So a sub% energy resolution on individual CRES events or individual electron decays is almost trivial with this CRES technique, and that's what makes it so powerful compared to a lot of traditional spectroscopy where you have to put in a lot of work and a lot of simulations to be confident that you are resolving events to the level of 1% or better. Okay, so that's kind of the high-flying overview of the progress that we've made to date. We've showed that this method can produce results. We've seen our first CRES signals, and I want to devote most of the rest of the talk to putting in or describing a lot of the things that we have done since seeing those first CRES signals in order to prepare ourselves for running with helium and helium-6 and also neon-19. So when you really get down to it, a lot of the work that we've done over the last 6 months, it really boils down to making improvements in our vacuum system, especially since we all got our vaccines and got a chance to get back in the lab over the summer. Even though the CRES technique works best with a source in the gas phase, it turns out that it's actually really critical to have very good control over the background gas pressure. And this slide shows you a little bit why that's the case. So you'll remember that as the electron loses energy, the frequency of radiation increases, and the frequency with which those jumps happen is proportional to the background gas pressure. So if you took a look at this spectrogram here and thought that looks fairly daunting to analyze, I assure you, you're not the first one. The task of track and event reconstruction is actually one of the most difficult things that Project 8 says they have to do, and I understand why. So rather than deal with lots of short, choppy little tracks, if we can remove as much background gas as possible, it will pay off in terms of a simplified analysis because we'll have fewer tracks, longer tracks that are easier to analyze, and it doesn't open us up to any potential systematics for short tracks that of an electron that might have been emitted and scattered almost immediately and then gone on re-radiating at a lower energy which would bias us towards low energy events and could easily be confused for a non-zero value of little b. So we put a lot of work into improving this vacuum system, especially over the summer. Initially, we had been running things into this turbo pump and then trying to get everything clean using this getter assembly. And it's difficult to pump with anything else because the CRES volume is, the CRES source is in the gas phase, and the decay cell is effectively a dead end. So we really want to be putting helium in there and nothing but, because the helium obviously will decay, and any contaminant gases will just chop up our tracks and make analysis much more painful. So over the summer, we've engineered this second stage cryotrap that's put in the line. It's about 30K and condenses most of your gases besides neon 19 or helium 6, and also this second much larger cryotrap that's off to the side and is mostly responsible for pulling off the junk that is adsorbed onto the stainless steel walls of this big long 8-inch pipe. So prior to the installation of these cryotraps, as I said, our vacuum quality was pretty bad, on the order of 10 to the minus 5 torr, and that went on for after weeks and months of baking and pumping and trying to get it down. Now with those cryo pumps, it's actually quite easy to get things down to the 10 to the minus 7 torr range. So we're hoping that our helium spectrum will look a little bit cleaner than the krypton spectrum or the krypton set of events that we had, especially with a deep trap. So again, that's what our vacuum system looks like in principle. Here's more of what it looks like in practice, complete with dangling power strips and lots of aluminum foil. Our helium 6 target and neon 19 target are on the other side of this concrete wall for shielding purposes. And then the source gases come down this large 8-inch pipe, get compressed by this turbo pump into the second stage cryotrap, through that cryotrap, and into some small pipes past some getter assemblies, residual gas analyzer and whatnot, and into the main CRES cryostat where the decay volume is just off screen here on the bottom right. Okay, so a lot of the work that we've been doing over the summer also revolves around the sources that we have for helium 6 and neon 19. I just wanted to give a brief description of how we're actually going about making those things around here, because I think it's worthwhile. We make helium 6 by bombarding a liquid lithium target with 18 MeV deuterons. That liquid lithium target sits inside of this apparatus, separated from the beam vacuum by a tantalum foil. And then the beam penetrates that foil, interacts with the lithium inside, and the helium 6 diffuses out and into that 8-inch pipe, eventually gets compressed into the decay volume. So over the summer, we pulled this source out and replaced both the tantalum window and the lithium source just to make sure that everything is good to go. It's been rewired, safe for remote operation, and we hope that we can get the same 10 to the 10 helium 6 atoms per second that we were used to with the previous MOT-based experiment. A lot of the other upgrades that we've been making over the summer have to do with manufacturing neon 19. It turns out that neon 19 is a very complementary source for our purposes because it's a positron emitter. So for any non-zero value of little b, neon 19 will have a distortion to the spectrum that's equal and opposite of that for helium 6. So if we observe, say, a surplus of events, helium 6 at low energy, we would expect a corresponding deficit of events in neon 19 at low energy, and that would help us distinguish, hopefully help us distinguish between some systematic that we weren't really appreciating and a true non-zero value of the Fears interference coefficient. So we go about making neon 19 by bombarding sulfur hexafluoride molecules with protons inside of this gas target. It's again spaced off by a foil from the beamline vacuum. So the fluorine atom will pick up one of those protons and become neon 19. And then the combination of neon 19 gas and SF6 gas is flowed through this cold trap, which is just a bunch of steel baffles that submerge in liquid nitrogen that will condense most of the SF6 and effectively none of the neon, because neon doesn't condense at those temperatures. And then again, just the neon is meant to diffuse out into our experimental region of interest. And it turns out that when we put this thing together for the first time, there were a fair amount of contaminant gases. We're not quite sure what they are, but they don't seem to condense at liquid nitrogen temperature. And so that was one of the primary motivations for this second stage cryotrap at 30 K to try to condense anything that will condense above the, again, above the condensation point of neon or helium. Okay, so once again, that's what the source looks like in principle. Here's what it looks like in practice. The actual gas source is right here, spaced off from the beamline vacuum by a couple of foil windows. And then this valve controls the flow of combined neon 19 and SF6 back to that cold trap that removes the SF6 and lets the neon 19 get into the room where we do the CRES experiment. Okay, so the last big area that we've been working on is improvements to our DAC system. So to actually digitize these signals at at gigahertz level, we rely on this FPGA setup that was actually developed by the Casper collaboration for radio astronomy. This was made for a bunch of radio telescopes. Like I said before, we have a couple of high-speed analog to digital converters that give us 8-bit samples at 5 gigasamples per second. And we can digitize those very quickly and write out an FFT every 54 milliseconds in order to stack those up to make our spectrograms. And the reason that we rely on this FPGA rather than trying to wire an ADC directly into our DAC computer is because the FPGA is capable of a tremendous amount of throughput. In this case, 10 gigabytes per second of data can come in and get pulled off of this guy. We're actually looking at more like 600 megabytes per second, which is challenging in and of itself as a data rate, just to make sure that we're not dropping packets. So everything is packetized and put onto the network by this Roach 2 system, and that's what enables us to get a consistent data stream for analysis. So this is just a conceptual overview of how we program our FPGA using the Casper libraries. It's actually a very convenient tool set for people who have no experience in Verilog or VHDL, any of the main languages that are used to program FPGAs directly. So it's just a block diagram similar to a lab view setup. You can see the flow of information through this FPGA on each clock cycle. These ADC blocks produce 16 8-bit samples. We can take some snapshots of them in the time domain, but mostly what we're doing is applying some time domain filtering, doing the FFTs, buffering it out, putting everything together into a bunch of UDP packets, and then broadcasting those UDP packets over a single 10 gigabit Ethernet output. So we get our data stream onto the network at about 600 megabytes per second. And that's good for about 1.2 or 1.4 gigahertz of observable bandwidth. So one of the actual challenges that we wanted to use this platform to try to resolve has to do with the Doppler effect. So you'll remember that in the principles of magnetic trapping, right, we have an electron that's going around in circles around some holding field, but it's always going to be emitted with some non-zero axial velocity. And those trap coils define a potential that will confine the electron, but it will always be sloshing back and forth according to the pitch angle with which it was emitted. And if you look at the cyclotron or the cyclotron radiation on the axis of the main field, what you're going to see is an electron that's going around in circles and periodically moving towards you or going away from you. And that periodic motion of the electron along the axis leads to a time-dependent Doppler shift. And so when you look at the signals on axis, you get this time-dependent Doppler shift, which is equivalent to a periodic frequency modulation in the signals. And when you look at the math of periodic frequency modulation, you'll see that what can happen is that the signal can be fanned out into a very large number, potentially very large number of sidebands. And those sidebands will siphon power away from the carrier. Effectively, the carrier can actually disappear if the amplitude of axial modulation of the electron is large enough, because mathematically it's referred to as the modulation index physically it's equivalent to the motion of the electron in the trap along the axis. And this is just a spectrogram that Project 8 uses as an example to illustrate this effect. This is again from Ali's thesis. And you can see there's an event here where the carrier frequency has all but disappeared, and all you can see is a pair of sidebands until the electron undergoes a scattering event, after which it moves to a different modulation index, maybe settles a little bit towards into the bottom of the trap, and then goes radiating with a more visible carrier and attenuation on the sidebands there. So obviously this is difficult, both from an analysis point of view and from a systematics point of view, because in the worst case scenario, large modulation index events spread their power out across a large number of sidebands. And if all of those sidebands are below the noise floor, we will not be able to see a given electron until it perhaps undergoes a scattering event, settles into the bottom of the trap, and goes on radiating with the lower energy. And that lower energy may be, if we're not careful, we can identify that lower energy as the creation energy of the electron, which would give us a bias towards lower energy events, which could very easily be confused for a non-zero value of little b. So we really want to take out this Doppler effect if it's at all possible and get all of the power into a single band that we can observe. So it turns out that one of the advantages that we have over Project 8 is a large bore magnet, and we use that to squeeze in a pair of amplifiers rather than just looking at an individual CRES electron signal from a single side on the axis. And this is actually very useful because, as the electron sloshes around in its magnetic trap, one amplifier is always seeing a wave train that's redshifted, and the other amplifier, because it's looking from the other side, is always going to see a wave train that's blue shifted by the same amount. So the total Doppler shift on each of these amplifiers is constant, or is actually zero. So what we can do with that mathematically, if we take the product of the signals from these two amplifiers, or the two ADCs, one of which is blue shifted, one of which is red shifted, we get components at the sum and difference frequency. And that sum frequency is twice the carrier always, because we're always looking at one red shifted wave and one blue shifted wave, and the magnitude of the shift is constant. So theoretically, this can get rid of the sideband problem and will give us an unambiguous signal at twice the carrier frequency. And the big drawback to this, unfortunately, there's always a trade-off. The big drawback to this is this factor of 1/2. So while we do get an unambiguous product, or some frequency signal, that signal is attenuated relative to the individual signals, and it's not clear that we can afford the power cut in signals and noise. So we can go back to the roach here and think about how to implement this. It's actually fairly simple. All we have to do is take pairs of signals from these ADCs and multiply them before we send them to the filter and the FFT and output them in terms of packets. And this is one of the big advantages of using FPGAs. It's very simple to implement this algorithm and thereby hopefully eliminate the Doppler shift as a potential source of systematics, although we had yet to actually try this because I didn't wire the ADC in right when we got our first set of krypton events. So I guess I would be remiss if I ended the talk without saying anything at all about systematics. Unfortunately, a lot of our systematics, I think, are probably going to come from the track and event reconstruction and the confidence that we can have in making sure that we can reconstruct all of our tracks into a single event. That's not particularly well understood because, like I said, we're just getting started with our analysis, having seen our first signals a few months ago. But one of the systematics that we have put a lot of thought into is the rate of wall collisions. So, like I said, the efficiency of magnetic trapping is independent of the energy. But what does depend on the energy of the electron is the cyclotron radius. So for a set of events, lower energy events have larger radii, and there are, as you can see with a finite size waveguide, events with large radii are much more likely to collide with the walls. And electrons that collide with the walls are basically lost instantly and will never be visible to our apparatus. And all of this can be, so we can be biased actually towards high energy events with smaller radii because there's more of them that can fit inside of a given cross-sectional area of our waveguide. And that can be backed out mathematically if we have perfect knowledge of the guide radius, but obviously our knowledge of the guide radius is imperfect. The thing is made out of copper. It's going up and down in temperature as it's expanding and contracting. And we really want to know, to be confident that we can back that out mathematically, we need, a submicron knowledge of the guide radius. So that is a potential source of systematics. In the long run, we want to remove that as a source of systematics by implementing an ion trap that will confine sources that are ionized rather than being just in the gas phase confined by this cylindrical guide, and that would hopefully take away this effect and also enable us to do CRES experiments on different species rather than ones that are in the gas phase at low temperature like neon or helium. But one of the other ways we can get a grip on this event this effect without implementing ion trapping is by exploiting the coupling of individual events with finite radii to the guide mode field. So this is just a schematic of the lowest order mode fields in the cylindrical guide on axis here. You can see that electrons that are radiating closer to the guide walls are more poorly coupled to these mode fields, and as such they radiate less power into our CRES apparatus. So we can extract some knowledge of actually where the electron sits in space from how much power that we observe. And in particular, these are the results of some Monte Carlo simulations we've done. This peak here is, I think, the line between the set of all events that include the guide center and the set of events that don't. And then as you move towards the center, you get more and more power. So we can start to fiducialize our waveguide volume in that way if we have better knowledge of how much power we're actually observing, how much power that's coupling into the guide. Okay, sorry. Okay, so the last part of the puzzle that I want to talk about is how to actually go about building a spectrum when all you can see is a finite frequency window. I admit I was a little bit hesitant to show you this plot because I've shown it a bunch of times before, and people often get the impression that we intend to leave these huge gaps in our spectrum just by taking data at 1, 2, and 3, and 5 Tesla, and that's not the case. We definitely intend to take data at 1 Tesla, 1.2 Tesla, 1.3 Tesla, and on and on. The point of showing you this plot was just to emphasize the point that for a finite bandwidth, you get a fairly narrow window in energy, and that window actually expands for a fixed frequency bandwidth. That window expands as you crank up the magnetic field and look at higher and higher energy events. But at the end of the day, we have 1.2 gigahertz of observable bandwidth to start. Our design spec was closer to 6 gigahertz, but even with 6 gigahertz, we're looking, especially in the low energy region of interest, we're looking at a fairly narrow slice of the spectrum at any given time. So in order to take a bunch of these subspectra, even if they overlap, we're going to have to shut the experiment down, put the leads into our magnet, crank the current back up, and boot everything back up. And the accelerator that's producing our Helium-6 is kind of a fickle instrument. It's not particularly stable in the amount of Helium-6 it produces from 1 second to the next. So we have to have some way of normalizing these subspectra and actually connecting them to one another to make one single complete object for our analysis. And for that, we need a good helium input flux monitor. And that's kind of the last big piece of the puzzle that we're really working on, especially one of our grad students has taken charge of building a Helium-6 input flux monitor that's based on these silicon photomultipliers or SIPMs. This is a cartoon diagram of a sandwich board setup that we want to read out the Helium-6 input flux by detecting betas going into the apparatus with some plastic scintillator. These red guys are the little SIPMs that are about 3 millimeters by 3 millimeters apiece, and they're kind of sandwiched together in this setup for the electronics and the readout. So, like I said, we also have a very narrow energy window for a fixed frequency bandwidth, and we want to make that frequency bandwidth as big as we can. But the roach here, that we are using, the FPGA that we're using to digitize our signals only has about 5 gigasamples per second on each channel. And so we're only running it about half as fast as it could be run. So we're only getting about 1.2 or 1.4 gigahertz of bandwidth with a single one of these guys. So we want to move to a more modern FPGA platform or radio frequency system on chip or RF SoC platform, like the Xilinx ZCU 111 that's becoming quite popular, especially amongst people who do software-defined radio and radio-defined experiments. So this thing has a set of 8 ADCs, each of which can do 4 gigasamples per second each. Unfortunately, that does add up to about 100 gigabits per second of output, which is about a factor of 20 faster than we are able to record data right now with a single machine. So there's quite a few challenges involved in scaling it up, but we can imagine chopping up our observable bandwidth, our 6 gigahertz that we want to observe into 4 1.5 gigahertz channels each, taking the signal from each amplifier and fanning it into 4 of these ADCs, and then observing 6 gigahertz of bandwidth at a time rather than 1.2 or 1.4, which will obviously make it much easier to get statistics, and will probably reduce the stringent constraints on how well we need to know the helium-6 flux from moment to moment as we take our data. And as I already said, hopefully we're able to implement an ion source and an ion trap in the future to constrain some of the source atoms in the center of the guide, and then get away from that wall collision effect as well. So that's kind of our plans for the short and medium term future. To try to wrap things up here, like I said, helium-6 is a good system to look for new physics, especially tensor couplings in the weak sector. We've been able to observe our first CRES events from individual electrons. We've built up our neon 19 and helium-6 sources, so we're ready to go with that. Once we can get our magnet cold again, which looks like it's going to be tomorrow, we are hopefully ready to put helium-6 inside and try to start getting our first real events. And with that, we can start moving towards doing some actual science. So these are all our team members, the folks at UW CENPA. I especially like to thank our grad students, Heather, Drew, and Winston, and all of the remote collaborators who are associated with Project 8. Like I said, we wouldn't have gotten anywhere near the level of progress we've been able to obtain if they weren't helping us basically every step of the way there. So with that, I'd be happy to open it up to questions.
Thank you very much, Brent. It's definitely a very exciting project, and looking forward to see the results. So questions, please, to Brent. So I can lead off because I have a question about this normalization issue. So I'm kind of worried. So you explained that you will be using the scintillator, and I'm a bit confused. So you are measuring electrons which are not trapped in this scintillator, right?
Yeah. So we're streaming helium-6 off of the source, and that's
right.
There's a certain number of those helium-6s are going to decay en route to the source. And if we observe all the decays, or some fixed fraction of those decays, that just gives us a sense of how hot the source is from moment to moment. So we don't need to observe the electrons that are in the trap. We can just need to observe how many helium-6s per second are moving towards the trap.
I see. Okay, and that has relatively small systematic uncertainty, right?
Hopefully, we think that we want to be able to make sure that we have part per thousand stability, at least for our kind of phase 1 experiment. We want to know the helium-6 flux to a part per thousand at any given time to be able to assemble this into a big spectrum.
I think it will be kind of challenge to reach that kind of absolute uncertainty.
Yeah, I mean, like I said, it's the last big piece that we're working on here. So
okay, so I see there are hands up, and Oscar Navilat, please unmute yourself and go ahead.
Yeah. Hi, Brent. Nice to see you again this week. I had a question about the trap. What kind of trap what kind of ion trap are you considering? Is that since you have a magnetic field, I guess the natural trap will be a penning trap, but what kind of ion trap do you consider?
Yeah, we're thinking about a cylindrical penning trap. Folks from Texas A&M would be better positioned to answer that than I am. But yeah, they have a cylindrical penning trap at TAMU, and I think they're thinking about implementing something similar for us. I think the real challenge is going to be ionizing the helium and directing it into the trap rather than building the trap itself. But making the cylindrical waveguide into a segmented cylindrical penning trap should be doable.
So there will be an ionizer just after the source for the injection?
That's the idea. Yeah.
Okay, good. Thank you.
Okay. More questions? I don't see anything in chat. Okay, I see Greg Chuparian, please go ahead.
Hello, thank you for a very interesting talk. I have a technical question. When the ions, heliums, are coming out from the target, they are flowing inside the volume, that's correct? Inside the vacuum.
Right.
And then after that, you are sucking them into the pump, correct?
Yep.
And are they sticking to the walls of the volume?
Well, I mean, the good thing about helium is it's not very sticky. So, you know, it's very hard to get helium to stay put. So, you know, I think one of the advantages of working with helium is that, you know, it doesn't want to stick to anything. Doesn't want to stick to the pump, doesn't want to stick to the walls, and it doesn't want to stick to this cryo trap at 30K.
Yeah, the cryo trap, it probably will not, but immediately after it is coming from the target and entering to the volume. Why I'm asking, because I've seen in a couple of places then people are intentionally heating up the, you know, the tubings and things like that to prevent, and claiming that doing that, they are increasing an order of magnitude the yield of the helium-6.
That's interesting. I guess I never thought that. I never thought that helium-6 or helium at all can be sticky for stainless steel. But
you mean ions, Greg, or neutral?
Well, as well, the helium, excuse me, most likely are neutral.
Yeah.
Yeah. Okay. Yeah, they shouldn't stick much. I wouldn't think either.
Well, I'm saying what I can try to find those papers, but I had like a couple of those. One was a report and another was a paper. So essentially, they are making, you know, like a corner loop to prevent them going straight, and they are heating the entire volume just for you know, preventing them to stick to the walls. Was my recollection. But I mean, it's just a question. So your experience shows that most likely they don't.
I don't think we
go ahead. Yes.
All
right.
To be honest, yeah. I'd be.
So I see another hand. I see another hand. Alejandro.
Yeah, this is I just wanted to comment, Greg. We've done measurements of the lifetime helium-6, and we were very concerned about something like that. So we did careful measurements, and stainless steel, there is really, you know, below, we put an upper limit on something like 10 to the -5 of the fraction that could attach some, you know, on a microscopic system like this.
Mm-hmm. Okay, thank you. Thank you, Alejandro.
Okay. Any more questions? I do not see anything in chat. I do not see hands. Okay, then that concludes our seminar today. And thank you. Let's thank Brent again. So thank you very much. Okay, and thank you everyone for joining us today. All right.
Thanks for hosting.
Goodbye.
Bye, everyone.